Now let's continue to study the power consumption in an RLC series circuit. We saw in the previous lecture that the power consumed by the resistor varies as a function of time, but as a time average, we can write it as 1/2 times the peak value of the current squared times R. And that is why we defined the so-called I effective or V effective. Now, the peak value I maximum itself is a function of omega, as you know. It is in fact given by I maximum equals V maximum divided by this expression which has L, R, and C and omega. You recall? Okay, so if I plot I as a function of time, as we did before, I'm going to get something like this. No, actually, I as a function of the frequency omega. Okay, so therefore, the power consumption by the resistor as a time average value should also have a similar expression. Okay, it is equal to I maximum squared over 2R. So it's proportional to I maximum squared. So it should also peak at the same point. And so if I were to plot I the power consumption time average on the resistor, I'm going to get a similar curve like that. Okay, so you see it peaks at a particular frequency, omega naught. This is the so-called resonance frequency. Not only is the current in the circuit the greatest, but at the same moment, the power consumption on the resistor also reaches the greatest value at the same resonance frequency. Okay, now, if we go further to study the power consumption on the inductor and the capacitor, what do we see? First of all, on the inductor. Okay, the inductor, the power going through the inductor is current times VL. You notice that it's the same exact current going through all the three elements, R, L, and C. So we use the same I. VL. Okay, so it's I times VL. This is I, right? It's I maximum times sine of omega t minus phase angle times VL. VL here is the maximum value of VL, the amplitude of VL. And there's a sine omega t minus phi, but don't forget there's also a phase difference of pi over 2. You know, VL leads the current going through the inductor by an angle of 90 degrees. Okay, now this I can rewrite as cosine function. Okay, sine of theta plus pi over 2 is the same as cosine theta. Alright, so basically this is proportional to sine times cosine with the same exact argument of omega t minus phi. Now, you know omega t minus phi is an angle that changes over time, right? In fact, if I plot a vector which makes an angle of omega t minus phi with the reference axis, then as time goes by, this vector will then rotate with an angular speed of omega, right? So it's going to go through the first, second, third, and fourth quadrant while completing the whole cyclic motion. Meanwhile, what's happening to PL? You know, if this angle of omega t minus phi, if this phase angle is in the first quadrant, then both sine and cosine happen to be positive because the product is positive. So PL is positive. Okay? That means when the time interval is such that omega t minus phi is within the first quadrant from 0 to pi over 2, the power going over PL is positive. That means during that time interval, the inductor takes in energy. Okay, it takes an energy from the rest of the circuit. Now, in the second quadrant, as t goes by, omega t minus phi will enter the second quadrant. Sine remains positive, but now cosine becomes negative, right? So the product is now negative, which means the power consumption by the inductor now becomes negative. What does a negative power consumption mean? Well, a positive power consumption means the element is taking energy in from the rest of the circuit, right? So now we have a negative power consumption. That means what? That means the element or the inductor is feeding energy back into the system, back into the rest of the circuit. Okay, so it is giving energy up back to the rest of the the rest of the system. And then you go to the third quadrant. Okay, when omega t minus phi is in the third quadrant, both sine and cosine are negative, right? So now you would have a negative energy consumption. Okay, and once again, it's feeding energy back into the system. Now, finally, you go to the fourth quadrant, and this is when, actually, when both are negative, I'm sorry, you should get a positive value, right? But in the fourth quadrant, sine is negative, cosine is positive. So now the product once again becomes negative, which means in the fourth quadrant, the inductor is again feeding energy back into the system. So you see, within the whole cycle, half of the time, okay, PL is positive, the other half of the time is negative. That means half of the time the inductor takes energy in from the rest of the system, but the other half of the time it gives energy back to the system. So what do you think is the average, is the time average power consumption over one cycle? Well, our intuition tells us it should be 0. And then indeed, if you do this power average calculation, you have to integrate over sine, cosine over one whole period. And this integral can easily be shown to be 0. As a matter of fact, you can move the cosine in. Don't you get d of sine? Right? You call this angle theta. Then it's basically sine theta times d sine theta. Okay, so that's 1/2 sine theta squared. Sine theta squared is a periodic function going over one period. Of course, the upper lower limits are equal, so then the integral is 0. Right? This is the mathematics. Now, physically, what it means? It means that over one whole period, the inductor does not take energy in. Okay? It does not really waste an energy. What it does is that it sometimes takes energy in, but sometimes it gives energy back into the system. It will never consume any energy, unlike the resistor. Okay. Now, similarly, for the capacitor, the power consumption of capacitor is I times Vc, and here's I, here's Vc. And you notice there's a subtle difference between Vc and VL. Instead of plus pi over 2, you have minus pi over 2. Okay, so sine of theta minus pi over 2 is the same as negative cosine theta. So now you still have a sine and cosine product, except you have an extra negative sign. So instead of plus minus, I now have minus plus minus plus. What does that mean? It means that just like the case of the inductor, a capacitor over one cycle spends half of the time taking energy in, but the other half of the time feeding energy back into the circuit. Okay, so overall you can see that the power consumption by the capacitor is also 0. Okay, but if you compare these two cases, you'll find that at any given moment when the inductor takes energy in, the capacitor is feeding energy back. Okay, and when the inductor is feeding energy back into the system, that is when the capacitor takes energy in. You know, that makes perfect sense. In fact, in an LC circuit without R, okay, without R, what happens? What happens is that you don't even need a EMF to power the circuit. The energy continuously flows back and forth between the inductor and the capacitor and the capacitor. So when the inductor loses energy, that energy is not going anywhere. It's not wasted. Rather, it just, it gets stored on the capacitor. And when the capacitor loses energy, the energy flows into the inductor. Okay, so one is of course electric form, the other is magnetic form. So there's a constant transfer between the electrical energy on the capacitor and magnetic energy on the inductor. So they just flow back and forth, but no energy is actually wasted into heat. Okay, now we have an LRC circuit. So there's something new. There is a resistor, and the resistor always takes electrical energy turns into heat, right? And therefore, to sustain the oscillation, you must continually feed energy into the system, and that is done by an EMF. But that EMF doesn't have to feed energy into the inductor and capacitor over one cycle. Rather, it only needs to feed energy to the resistor. And just like before, the inductor and capacitor never consumes an energy as a whole over one entire cycle. Rather, they just temporarily store energy and then give energy back a time later. So that's what they do. So overall, for an LRC circuit, when it comes to power consumption, the only element that we have to consider, okay, as something that consumes energy is the resistor, as usual. So let's go back and plot the same thing here. This is the average power consumption for the entire LRC circuit in series. That in fact equals the average power consumption on the resistor, okay? Because again, the inductor and the capacitor over one cycle, they do not consume any energy. So power consumption equals that on the resistor as a time average. 1/2 I maximum squared times R, okay? And then we can write I maximum as V maximum divided by the square root of this thing. Remember, that's how we solved it with the phasor method. Okay, you have to square it. So this is what I get. Okay, it is certainly a function of LRC and a function of omega. It peaks at the resonance frequency omega naught. Again, what's so special about that frequency? At that frequency, VL and VC have the same magnitude, but they always are out of phase by 180 degrees, so they add up to 0. Okay, they cancel out. The entire EMF will be entirely borne by the resistor. That causes the greatest possible current going through the resistor, and therefore causes the greatest possible power consumption by the resistor. So that's why it peaks here. Okay, it peaks here, and this, of course, is when the circuit is a purely resistive circuit. Now, the shape of this curve. There are two important things when it comes to the shape of this curve. One is, of course, where is the peak, and that is omega naught, and that is controlled by L and C. In fact, omega naught equals 1 over the square root of LC. Remember. But another important feature is how wide is the peak. Okay, you can understand qualitatively what controls the width of this peak. You know, the reason why there is a curve like that, the reason why omega matters, is because of L and C, right? Because both of these elements will react differently to different frequencies. Okay, but the resistor doesn't really care about the frequency. Whatever frequency of the current, as long as you have the same peak value, it's going to consume the same amount of average energy. Okay, 1/2 I maximum squared times R. That has nothing to do with omega, right? So if there were only a resistor, what do you think this curve would look like as we change the frequency? Well, the frequency doesn't matter, right? So it's going to be a flat line without any up and down, right? So you can imagine, as I increase the resistance, the curve is going to become flatter and flatter and flatter, eventually become independent of omega when R goes to infinity, or when you just take away L and C. And similarly, if I make R smaller, then what happens? Well, two things happen. One is the curve becomes sharper, okay? Because R is the element that doesn't care about omega. The other two elements, L and C, do care about omega. So it's going to depend on omega more sensitively. It's going to go up and go down more sharply. And secondly, the peak value, okay? The peak value is going to rise, because the peak value at this point is when omega L equals 1 over omega C. So that term is gone. What you have left is V maximum squared over R. Okay, but you know what that is, right? When R is really small, V maximum over R, V maximum squared over R becomes really large. So you're going to see a rise. Not only is the curve going to be skinnier, shall we say? Okay, because not as flat, but also the peak is going to rise. So as R decreases, I'm expecting something like that. Okay, it's going to peak at the same frequency, but becomes narrower. Okay, it's going to become narrower. Now, when is a narrow curve more desirable? As we discussed briefly in the previous lecture, a narrower curve means the system will respond more selectively. Okay, it responds to this omega naught. It doesn't really care that much about other frequencies. It drops quickly as the frequency goes away from omega naught. It's a more selective circuit, and that will be useful when we design a receiver to receive electromagnetic signal, okay, so that it can zero in on a certain frequency and reject other signals. Now, we can quantify just how sharp this curve is. Okay, you see, as you move away from omega naught, as omega goes away, in either direction, it's going to go down. The power consumption is going to go down, right? Let's say here is the peak value of the power consumption. How far do you have to move, either to the left or to the right, before the power drops to half of the peak value? So half the peak value, right? See here. Well, it turns out you have to go this way and that way. It's not entirely symmetrical, but you will be able to find two frequencies. Here's omega 1, here's omega 2. Such that when omega equals either omega 1 or omega 2, the power consumed is this value, which is half of the maximum value, which equals to V maximum over 2R. Alright? That's when this term equals 0, of course. And you can easily solve omega and omega 2. All you have to do really is set this power equal to what? 1/2 of its peak value, right? So 1/2 of Vm squared over 2R. Then you can solve this equation. It's a quadratic equation. That's why you get two roots, omega 1 and omega 2. And you can find how far they are spread from here to there. And this spreading is called delta omega. Okay? The further it is spread out, the fatter the curve is, or the less sharp it is, right? Now, what we can do then is to define something called a quality factor, Q0. It is defined as omega naught over delta omega. So what again is delta omega? Delta omega is the frequency difference between these two frequencies, omega 1 and omega 2, such that at either of these two frequencies, the power consumption in the circuit is half of the maximum value at resonance frequency. Okay, you can imagine when delta omega is very small, Q0 is large. So the quality factor rises when the curve, when the power consumption curve becomes sharper, or we say skinnier. Okay, so high value of quality factor means it is a highly selective circuit which responds sharply to one frequency and rejects other frequencies. A low value of Q0 means it's a more flat response. It responds more or less evenly to various frequencies. Okay, this of course, this quality factor is a dimensionless constant. Okay, it has no dimensions, omega naught over delta omega. We can calculate that, okay, by solving omega 1 and omega 2, and we can, and after some algebra, you can easily find these values, omega naught L over R. And look at this, it's interesting to see what the value is. Look, if R equals 0, what does that tell you? When R equals 0, quality factor goes to 0, infinity, and that means the curve is infinitely sharp. Okay, infinitely sharp. Delta omega approaches 0. And that makes total sense, once again, right? Because when R is equal to 0, the only element that has nothing to do with, that doesn't care about the frequency, is gone. You only have L and C. And the system becomes extremely sensitive to the frequency of the driver, and when you drive it at resonance frequency omega naught, okay, remember R is already 0. When you drive it at resonance frequency, omega L minus 1 omega C also equals 0. So there is nothing left in the denominator, which means the power consumption goes to infinity. Okay, it goes to infinity. It's a curve like this, extremely sharp, but infinitely tall. That is when the quality factor goes to infinity. So basically, the quality factor is a quantity that measures the selectiveness of the curve. Okay, the greater the power, the greater the quality factor, the more selective this system is, because and that means it's got a sharper resonance curve. Okay, and in mechanical oscillation that we studied in physics 1B, there is something similar, also called quality factor, and you know, it means something very similar. Okay, so again, the higher the quality factor, the more selective the resonance is. So the resonant peak becomes very pronounced, very sharp. But different systems have different numerical value for this quality factor. A typical mechanical system, we may look at a quality factor in the, you know, say 5, 10, or 20, something like that. Okay, in an electronic circuit, the quality factor can become much greater, can be a few thousand or even more. But in an atomic system, okay, look at hydrogen atom, for example, the quality factor of this atom, as you know, if you plot its resonance curve, can be more than 1 million. Now, what does that tell you? It tells you that hydrogen atom will respond only to a very specific set of values of electromagnetic oscillation. Okay, if the frequency is wrong, it totally rejects it. If frequency is right, it absorbs it. It gives you a large response. So these are extremely sharp resonance curves. Why is that? Well, that has to do with the atomic structure, and you will see that when we study physics 1D. Okay, but suffice to say that the quality factor can vary a lot, a great deal, depending on the system that we study. Okay, before we end our discussion about the power consumption, I'm going to introduce a concept called a power factor. Now, what I'm going to do is I'm going to rewrite this expression a little bit. Okay, I'm going to rewrite this expression as P average equals 1/2 I maximum times another I maximum, which I write as VR over R, right? The voltage, the amplitude of voltage across the resistor divided by R. That's Ohm's law, and then times another R. I can always do that, of course. Okay, so that's 1/2 I maximum squared times R, just like that. But this VR, okay, that's the amplitude of the voltage across the resistor. I can find it from the phasor diagram that we used before. Okay, now you recall from the phasor diagram, here is the VR phasor, and here is the sum of the VL and VC phasor. The magnitude is VL minus VC. You add them all together, you get the phasor for the epsilon vector, right? For the EMF, right? And you know there is an angle phi between them, the phase angle between them, phi, and therefore you notice that Vm is just equal, actually VR is just equal to Vm times cosine phi, right? Times cosine phi. Okay, so what I'm going to do now is, instead of VR, which I usually do not measure directly, rather I'm going to express in terms of Vm, the amplitude of the EMF, which is VR times which is VR divided by cosine phi, or VR equals Vm times cosine phi. So I'm rewriting this as 1/2 I maximum V maximum cosine phi divided by R times R. So that's gone. Okay. And this expression is interesting. First of all, this 1/2 here comes from the time average, right? Time average. And then that's where we know it come from. But also it's proportional product of the maximum current and the amplitude of EMF. That all makes sense. But on top of that, there's also another factor, cosine phi. And if this cosine phi is a maximum value, we know the power consumption average is the greatest. And the cosine phi is 0, then there is no power consumed. This phi, again, is the angle between VR and Vm. It's also the angle between the current phasor and the EMF phasor. We call it the power factor, okay? Power factor. And when does the power factor reach a maximum? Which is 1. That is when phi equals 0. That, according to the phasor diagram, is when VL and VC have the same magnitude. They cancel out, okay? This is when the EMF phasor and the VR phasor totally coincide, right? And that, of course, we know that is resonance, okay? That is when phi omega equals omega naught. So again, that's when cosine factor goes, the power factor goes maximum, the power consumption is maximum. It all makes sense. And when cosine phi equals 0, that is when phi equals 90 degrees, right? Okay, from this phasor diagram, when does this angle reach 90 degrees? Okay, so you have to take that Vm, you have to turn it over there so that becomes 90 degrees from VR. You know that can only happen when VR equals 0. Okay, that can only happen when VR equals 0. So because tangent phi is VL minus VC divided by VR, and when tangent phi equals infinity, or VR equal to 0, that is when phi equals 90 degrees. And then when is VR equal to 0? That means there is no resistance. Okay, so you have a purely non-resistive circuit, and then of course that circuit has no power consumption, right? Because nothing is turned to heat, and therefore the power consumption on average would be 0. Okay, so it makes sense in either special cases. That is the idea of the so-called power factor.